voltage sources. That's why I'm saying, the example 1, and I'm starting with having or using 2 voltage sources. One source is required to supply current or voltage to the collector of the transistor, and the other voltage, the VBB, is required to have the voltage applied to the base. Remember that in order to place a transistor in the active region, the base emitter must be, it's a must condition, must be forward biased, and the base collector must be or is the reverse biased. By using the 2 voltage sources gives you, some flexibility of adjusting actually the Q point of a transistor by simply changing one of the 2 voltages, in this case by simply changing the VBB. And I will show you how we can modify, how we can adjust actually the position of the Q point for a given circuit. I'm making the assumption that the RB and the RC are already given, are already defined, and that's why I'm giving, the applications or the flexibility of using 2 voltage sources instead of a single voltage source. Now I will try to use a different color because I will I'll make some other small drawings that helps you to understand how we can approach or how we can solve those circuits. I mentioned that a common emitter, you notice that I'm having the emitter terminal of the transistor as a common connection or a common terminal in the input, and I'll make the input loop, and the other loop is on the output or on the collector. Applying KVL, that's the KVL that is applied in those 2 loops, we'll end up with the equations that are required to solve the problems. Now let's have a look on the input loop. We have we can write the KVL in the input loop as the VBB is being equal with the VRB, the voltage across RB, plus the draw voltage between the emitter and the collector, that's the VBE, plus the VBE. Okay, now I'm trying to define what means the VRB or the voltage drop across the resistance that is connected to the base. That's the IB current multiplied by RB plus the VBE. Now I'm trying to find the value for the VBE, which is actually equal with the 0.7 volts. Remember that the condition to place or to use a transistor in the active region is the base emitter junction must be forward biased. Means that replacing the VBE with 0.7 volts, and I'm looking for an equation that is in order to find the IB. From this equation, the IB is the VBB. Okay, that's the VBB minus the VBE divided by the resistance RB. Okay, now I'll try to clean up a little bit this part here, and that's why I'll delete this okay. Now remember that the VBB it's given in this example as 1 volt. The VCC is 10 volts, and to find the IB is the VBB minus VBE divided by the resistance that is connected to the base, which is 1K. That's 1 volt, the given voltage, voltage source that is connected to the base, minus the 0.7 gives you the 30 microamps, the current that is in the applied on the base. Means that the current that flows to the base, that's the IB, is 30 microamps. What else we know? We know that the beta, or the gain in current for this given transistor, for this given circuit, is equal to 100. The second useful equation is the relationship between the IB and the IC. And by definition, I'll put it aside, the beta is equally the ratio of the IC over the IB. You notice that the beta is a dimensionless number, being a ratio of the two currents. The equation that it's used to find the IC. Once you know the IB, you notice that I found the IB. To find the IC, or the current that flows into the collector. Now I'll put aside, the current that flows to the collector. That's the IC. There you go. The IC is the beta IB. Multiplying beta 100 with 300 microamps gives you a current of 300 milliamps. You notice that, and I mentioned from the beginning, that's a current control device. Means that adjusting or changing the base current, I will change the current on the collector. The other loop, or the output loop, that it's used in analyzing the circuit or finding the Q point, is the collector loop, or its name, the output loop. You notice that on the output loop, if I'm looking for the equation, what I'm seeing that the VCC equals with the VRB plus the VCE, or the voltage between the collector and the emitter. That's the voltage VCE. Okay, here we go. Sorry, the VRC. Sorry for that. The VRC, that's the RC resistance, plus the voltage between the collector and the emitter. Okay, once you know the current, the IC current, we can determine what is the VRC. And I put that in writing. That's the VCE. That's the second quantity that is required to determine to define actually the Q point of a circuit, of a transistor that is placed in a circuit, as the VCC minus the VRC. Now the VRC is equal with the IC multiplied by RC. That's the current that flows to the collector, or the current, the collector current multiplied by the resistance RC. That's IC, that's 30 milliamps multiplied by 100 gives you the voltage as the 3 volts, the VRC. 10 volts minus 3 volts makes the VCE, or the voltage between the collector and the emitter, as 7 volts. You may find, in some problems that is required to determine the saturation current. The saturation current, again, can be found, from the same output loop. When the current is the maximum in this circuit, but again, keep in mind that the saturation current is related to this circuit and has to be always less or equal with the IC max from the specs of the transistor. Usually I will remove that equal sign, because I'm not trying to push the semiconductor to the maximum current. always, I'm choosing the saturation current for a transistor less than the IC max. As I mentioned, usually it's about, 80% of the maximum current. Again, that maximum current, the collector maximum current, can be the typical, the minimum, or the maximum. If all three currents are given, I'm choosing, the minimum current. Now, we determine that the IC saturation as the VCC, but in top of that, I'm having, the collector and emitter voltage. That's the VCE saturation. Now, in notes, I made an example and I specified that it's minus the VCE on saturation. This value, the VCE on saturation is very small, around 0.2 as the average, can be anywhere between 0.1 and 0.4, 0.5 volts. But if I'm comparing 0.1, 0.2 with the VCC, I can neglect the saturation voltage. Means that I'll make the saturation voltage as being almost 0 volts. That's why I'm trying to simplify our calculations, and I'm assuming that the VCE saturation is 0 volts. That's why it's not part of the equation, but strictly if we have to make the precise calculation, I'm choosing the VCC minus the VCE saturation as 0.2. But again, in our applications, I'm choosing the VCE saturation as the 0 volts. The saturation current, which is defined as the maximum current that can flow through the resistor in this circuit, again, has to be less than or smaller than the IC max, which is the maximum current that flows through a transistor. Now, I will try to recall again the characteristics of the transistor, and I will try to plot below the okay, that's the VCE, and that's the IC or the collector current. The question is how we can define the two limits or the two extreme points in order to draw the load line. Now, if I have to choose, the intercept of the load line on the x-axis, that's the VCE maximum. What is the VCE maximum? The maximum voltage between the collector and emitter. The maximum voltage between the collector and the emitter occurs when the collector current is equal to 0. Means that the maximum voltage that can be applied between the collector and the emitter, and that's the voltage between the collector and the voltage between the collector and the emitter, when the IC equals to 0, means that the transistor is in cut-off region. If the IC is 0, there is no voltage drop across the RC, means that the VCE max is actually equal with the VCC or the supplied voltage. Means that I can choose, the VCE max as being equal with, the 10 volts. That's, the VCE max. On the opposite side, or the intercept of the load line on the collector or the y-axis, that's actually the IC saturation. And you notice that that's the IC, the VCC over the IRC. That's, the IC, and I'll define the IC saturation as the VCC minus RC. Okay, and I mentioned that has to be less than the maximum current. Now, drawing the line between the 2 points. Suppose that I'm trying to connect the 2 points. That's, the power the load line of the transistor of the circuit actually, and having the transistor in it. And this example, suppose that the transistor has 300 microamps, which makes a voltage. If that's 10, I'll say that's about 5. I'll say that's probably around the 7 volts. That's about 7 volts, which makes a current, or the corresponding current, which is 30 milliamps. That's 30 milliamps. Means that this point, which has the two coordinates, the x is the 7 volts, and on the y the IC has the value of 30 milliamps, and that's the Q point of the transistor of the circuit. You notice that is not an ideal for the functionality of the circuit. Again, if I'm superimposing, or if I'm applying an input signal or an AC voltage on the load line, if the swing of the input signal is larger than the few hundreds of microamps, the output voltage and the output current, it will be clipped. Now, suppose that, and that's again the advantage of using this diagram. Suppose that I'm having a variable voltage source, and this is what I'm doing now. I'm changing the voltage source as a variable voltage source, and suppose that I'll try to push the Q point closer to this saturation. Suppose that I'm trying to make the Q point of this transistor closer to the saturation region. Means that I'm pushing the collector current close to the saturation value, and you notice that at this point the VCE becomes smaller. Now let's make I'm trying to make if I'll try to make 900 microamps. I'm going in a reverse way. Means that the difference 0.9, I'll make 1 volt as the 1.6 volts. 1.6 volts minus 0.7, it's 0.9. 0.9 divided by 1K makes 900 microamps. If the current is 900 microamps, the IB makes the collector current as 90 milliamps, which is just a bit below the maximum or the saturation current. Means that the current that is, let's say, 90 milliamps. 90 milliamps is just a bit below the saturation current, which makes the VC or VCE 90, that's 9 volts. We makes the VC as 1 volt. That's 10 minus 9 makes 1 volt, which is 1 volt in this region. You notice that in both cases the Q point is placed close to the cutoff, that's the cutoff region. On the second example that I made, the Q point, or the new Q point, is placed closer to the saturation region, which is on the left side of the graph. Means that if the Q point is close to the cutoff, that's the cutoff region, and the other one is the saturation region. Means that is not an ideal, but now let's try to make some changes, and I mentioned that most of the time, and I may choose a different color. Which one? Let's choose green. Suppose that I'm trying, to place the transistor somewhere in the mid-range of the load line. And that will make, probably about, 5 volts and let's say 50 milliamps and about, 5 volts. Means that I have to change the supplied voltage instead of 1.6. That's why I'm going in reverse way. I will choose the 1.2, which makes the base current as 500 microamps, which makes the collector current as 50 milliamps. And in this case, that's 50 makes the VC as the 5 volts. That's not an ideal case. That's an ideal design for the circuit in order to place the Q point somewhere in the mid-range of the load line. Now, the disadvantage of this circuit, remember that using 2 voltage sources, not always are available 2 voltage sources. Most of the time we are using, a single voltage source. And that's why I grouped with the example 1 with example 2, which uses, the same circuit, except that instead of using the VBB, I'm connecting, or I'm choosing, the same voltage source for the base voltage. Means that the circuit that is required to use a single voltage source has the RB/RC. And I mentioned that because the VCC usually it's a large voltage, 5, 10, 20, 50 volts and so on. The VRB is a pretty large resistance. I said that, tens, hundreds of mega ohms. So you may see like in lab, I'm using 200, 300, 400, 600 kilo ohms resistance, because the VCC, or the voltage that it supply the collector and the base, it's pretty large. Now, basically the same equation, except that I'm not having the VBB. Means that in the main equation here, when I'm using the VBB to find the IB current or the base current, I'm substituting the VBB with the VCC, because I'm using just a single voltage source. And again, I'm applying, the KVL on the input loop, and the KVL on the output loop stays the same, because nothing was changed on the output loop or on the collector emitter loop. Means that the only change that is required to solve the circuit or to find the IC and the VC is the substituting the VBB with VCC. Means that I'm applying, the same equations. Again, that's, just the KCL, just a different notation applied for the electronics, for the electronic circuits. The VCC minus the VBE divided by RB. We know that VBE has to be, or it's equal with the 0.7, because has to be or must be for bias. 10 volts minus 0.7 divided by 93 makes 100 microamps. 100 microamps multiplied by 100 of the beta makes the base current as the collector current as 10 milliamps. Now, the other quantity or the other coordinate of the Q point, remember that finding the Q point is finding the IC and the VC, which will define the Q point of the transistor of the circuit. Is the same identical equation, VCC minus ICRC, which gives the a voltage of 9 volts as the VCE. Saturation current, the same equation, nothing is changed on the output loop, the VCC over the RC, which makes the current of 10 amps. I mentioned that disadvantage, or the biggest disadvantage of this circuit, is very simple. That's the advantage. Uses a single voltage source. That's another advantage. disadvantage of this circuit is beta dependent. What that means that and I mentioned and I put that in my notes, as the temperature is increasing the temperature is increasing, it will increase the beta, or the electrons becomes more agitating, increasing the beta, it will increase the IC. As the IC is increased, you notice that in order to find the VCE, the IC multiplied by RC, IC is increasing, which will cause the VCE to decrease. Means that the VCE, or the transistor, is pushed to the saturation region. That's a disadvantage. In order to compensate this disadvantage, is adding a resistor in the emitter, and that's the circuit that is called the emitter feedback, or the compensating resistance on the emitter. Now the name of the circuit is again emitter feedback bias. Now the same circuit, 93 100 ohms, but this time I'm adding a resistor in the emitter. Now what is the approach? This circuit has a different approach. Now, I mentioned that we can determine, and that's the equation that is given for the test, for the second test, actually, just a single test in the BJT and the Zener diode. In order to find the IE, or to find the current that flows through the the IE, or the current that flows to the IC, that's the IC, is beta VCC minus VB over the RB plus beta RE. Again, from where is coming this equation? Actually, I'm not going to demonstrate, but I'm showing from where it's coming. Actually, I'm trying to substitute the IC from as the beta IB, and I'm expressing the IB as the VCC, and is based on the above equation, VCC minus beta RB VR minus VBE over the RB, and I'm substituting the IB in the beta IC, and I will end up with the IC, or the IE, as the beta VCC minus VB over the RB plus beta RE. That's the first step. Means that the first step for this circuit is finding IE, and now we are working backwards. Once we know the IE, means that the first quantity, the IC, which is the same with IE, is given. That's the second or the third assumption that we are making for the transistors. And to find the VCE, that's a change in finding, again, in the output loop, applying the KVL, which is the VCC, and I can write it aside. That's the the VCC equals the draw voltage across RC, draw voltage across RC, minus the VCE minus the draw voltage across RE. There you go. Now, from this equation, I'm looking for the VCE. VCE is the VCC minus the VRC, and minus the draw voltage across the resistance RE. Now, I'm trying to define what is the voltage, the VRC, and that's the RCRC, and the VRE is the IERE. But we know that the two currents are the same, means that I can simplify this equation as the VCC minus IC multiplied by the sum of the two resistances, RC and the RE. Again, the IC and the IE are the same. And that's why I can factor it out, and I'm having the IC, RC plus the RE. which makes the collector voltage, the collector emitter voltage as 3.5. In top of that, you may be asking for circuits like this or previous circuits to find what is the VB, VC, and the VE. You notice that again, it's a single subscript, means that are the voltages with respect to ground. Means that I'm looking to find the voltage at the base with respect to ground, the voltage at the collector with respect to ground, the voltage at the emitter with respect to ground. Remember, we made these first measurements in the first and the second lab in this course, which helps to have an understanding of those voltages. Now we will be able to calculate those voltages. Now for the VB, you notice that for the VB, again, I'm applying the KCL in this inner loop, and the voltage that is applied at the RB, that's the VCC minus the drop voltage across the RB. That's the drop voltage across the RB. That's the voltage VRB. Knowing the VCC, I can express the VRB as the IB-RB. Now the question is, how can we determine the IB? But initially, we determine the IC or the IE, means that knowing the IC, knowing the beta, we can find what is the base current. Knowing the base current, we are going back to the main equation, and we can find that the VCC minus the VRB is 3.5 volts. Means that the voltage at this point with respect to ground is 3.5 volts. To find the VC, again, that's the voltage at the collector with respect to ground. Pay attention in these calculations. That's the VCC minus the VRC. Now, if I'm looking in this output loop, that's the VCC minus the drop voltage across the RC. That's the voltage across RC, which will define the VC as the collector voltage or the collector potential with respect to ground. Okay, and the other one is the VE. That's the emitter voltage, and that's the emitter voltage. That's the emitter or the VE with respect to ground. You notice that it's actually the voltage across the RE. That's the VRE, which is actually equal with the current that flows through it. We just determined that in the first step. That's 6.99 multiplied by resistance value, which is the 400 ohms, makes the 2.8 volts. To calculate the saturation current, again, I'm looking in finding the saturation current or making the collector emitter voltage as being equal to 0. That's the saturation voltage or the saturation collector emitter voltage, which makes the voltage VRC plus the VRE as being equal to the VCC. From this equation, we can determine the maximum or the saturation collector current as the VC. The RC is from the previous equation. What we have to add, the new resistance that is present in the emitter of the transistor, which makes a current of 20 milliamps. Any questions up to this point? Because I will start talking about the last example. Now, the advantage, again, is pretty simple, but does not give too much flexibility in adjusting the voltage at the emitter. Means that I can change the RB in this circuit. I can change the value of the RB, but in the same time, I'm changing actually the current that is supplied to the base of the transistor. Means that another easy way actually to adjust just the voltage VB, it's using a voltage divider circuit. And that's the fourth example. If I will cover or if I will remove, let's say, the RB and I'll try to see if I can remove, this portion of the circuit. Let's say I'll delete it. You notice that the voltage divider bias derives from the previous circuit. What I'm adding actually just the resistance in the emitter, and the circuit becomes the R1 series with R2. And remember that in order to make the circuit as a stiff divider or voltage divider, I have to make sure that the IB is much less than the current that flows to the R1, R2. If this current IR1 or the IR2, let's say, is 100 milliamps, IB is at least 10 times less than 100 milliamps. Means that I can go closer to 10 milliamps as the IB. Usually it's much smaller than 10 milliamps, or it's smaller than 10 times of the voltage divider of the circuit. That's why the only condition is to have the IB much smaller than the I1 or the I2, which the I1 is the same with the I2. Means that this current, the IB, has to be at least 10 times smaller than the I1 or the I2. The two currents, the IB and the I2, what that means, has to be smaller. Means that in our calculations, the IB does not count or does not affect actually the calculation for the VB. That will be the first step in starting to analyze or starting to solve, the circuit that has a voltage divider, which is actually a series of R1 and R2. And in order to find what is the VB, the R2, I'm using the voltage divider rule as the resistance in question over the sum of the two resistances multiplied by the VC. Means that the VB is actually the voltage across R2, which makes the VB, or the potential voltage applied on the base, as 2 volts. Okay. Now, from the base, that's the base voltage on the emitter. What we know, the base emitter voltage is the 0.7. That's the base emitter as the 0.7. Or the emitter voltage is the base voltage less by 1.7 volts, knowing the VB. Means that knowing the VB as 2 volts, VB is 0.7, makes the VA as 1.3. Once you know the VE, for a given resistance, we can find the current that flows to the emitter. Means that I can define the emitter current, or the current that flows to the emitter resistance, as the voltage VE divided by RE, which makes 3.25 milliamps. But we know that the two currents, IE, is equal or is the same with the IC. Means that at this point we can find the second quantity for the Q point, the VCC, the VEE, as the VCC minus IC RE plus the RC, which makes 8.38 volts. Now, in order to find, and you notice that the flow of this problem and the other problem. Once we know the IE, now we are going backwards to find what is the IB. Means that knowing the IC or the IE, knowing the beta, we can find the, probably in milliamps, that's 3.25. And the IB current is in microamps, 32.5 microamps, because in the IC, 3.25 milliamps is divided by 100, which makes 32.5 microamps. The VC means that's the voltage at the collector. I am applying again the KVL on the output loop on this loop. Means that we can find the VC or the potential at the collector with respect to ground as the VCC minus drop voltage across the resistance RC. Now, drop voltage across RC is the ICRC, which makes 9.68 volts. To find the voltage VE, again, I explained that the VE is actually the voltage across RE. And we just determined that the voltage across, or the VE, is 1.3 volts, or we can do it in reverse order. Suppose that we know, or it's given the IE. Knowing the IE, knowing the RE, we can find the voltage as 1.3. The saturation current. Now, the same equation as the previous. You notice that again, there is nothing changed in the output loop from the previous circuit. Means that the output loop stays the same. What is changed is the input loop, which adds, just another resistor in the base of the transistor. Means that to determine the saturation current, that's the VCC over the RC plus the RE, which makes the same value. You notice that nothing was changed on the output. Now the question is, suppose that I already determined the VCE for the Q point and we know the IE. What will be the minimum power dissipation, or how we can choose a transistor? And that's why I put, in this problem, how we can choose a transistor that can handle or can be used, in a circuit like that. Means that the requirements are, the VC 8.38 and the IE, or the collector current or the emitter current, is 3.25. To determine the minimum power dissipation of the transistor, I'm choosing the IC at the Q point and the VC at the Q point. That's why you may see this notation to determine the minimum power dissipation that is required for this transistor, which is 27.22 milliwatts. That's, at the Q point. Doesn't mean that that's the maximum power or the minimum power of the transistor. Usually for this value, I will choose at least 30 milliwatts. At least 30 milliwatts is kind of pushed to the limit. If it's possible, probably a better choice will be 50 milliwatt transistor. I can go a bit higher, nothing wrong with that, but I cannot go lower than 27.2 milliwatts. That's why in choosing the transistor, we are looking for, and I mentioned that I'm looking for the collector current. That's the maximum collector current. I'm looking for the VCE maximum voltage that can be applied. And another parameter is, the PD or the PD max. Keep in mind that always look for the current, look for the voltage, and the power dissipation. Those are the three main components that we are looking for in using a semiconductor, and not only in using, electrical devices, electrical components. Current, voltage, and the power dissipation. Those are the three key quantities or values that we may look in the specs of the transistor. In the same time, looking for the beta, because we use the beta as equal of 100, means that I can use, any transistor that is in this range, 100 to 100, without making, you know, a huge difference in our calculations or in our circuits. Any questions at this point? Again, I will post, you know, these examples in detail. I'll brush it up, I'll clean it up again, and it will be posted probably in this week as an example, which helps you in solving those problems for the assignment and for the test. Any questions, please? Or if you have any questions related to these examples, you can ask me on Friday morning before I'm starting with the another topic related to the BJTs, and we'll start from there. Any questions, comments, concerns, please? If you don't have any questions, have a nice day. Thank you, guys.